to this video. My name is Abo Simon, and in this video, I'm going to be taking you through machine learning, basics of machine learning. So, without further ado, let me dive in. So, we begin. What is machine learning? I would say machine learning is the ability of a computer to learn and perform a task without being programmed to do that specific task, but it learns to do that task based on experience of doing the previous tasks. So that's what I think, or that's what machine learning is. So why do we need machine learning in the first place? We all know as we are programming, there are complex tasks that require a number of rules to be written to accomplish that task. So in this case, you cannot use our traditional programming to like accomplish that task. Yet you have to write like a lot of rules. So that's why machine learning comes in to like where you develop an algorithm that works in a way that it can learn and perform tasks without being necessarily programmed to do those tasks. So that's why we need machine learning. So there are two types of machine learning, that's supervised and unsupervised machine learning. Supervised machine learning deals with labeled data. This labeled data is labeled by humans. We are the ones that actually label it. And then we have unsupervised data, which deals with unlabeled data. So an example of supervised where it's applied, we have in predicting house prices based on like features like the size, the location of the house, and then we have an example in supervised machine learning. We have detecting or predicting the behavior of what the behavior of a customer, like whether they can buy a product that is beyond their pay grade. Yeah, basically unsupervised is used for that. And we have like two major things used by these learning algorithms or machine learning types. We have classification used by supervised learning and clustering used by unsupervised machine learning. So these are used to like categorize the data set, and as you can all see here in the graphs and the images here, categorizes them according to like the specific features. Then we have more about supervised machine learning, where we have regression and classification. Classification deals with categorical data to categorize data that is exclusive from each other, data that cannot happen at the same time, like data that is not in the same category, that doesn't have any relation. Then we have regression. It handles continuous data types. For instance, like forecasting stock prices and predicting temperature. These are continuous data variables. So we go on to unsupervised machine learning. Like I said earlier, it uses clustering to group features that show the same characteristic. Like I said earlier, it also deals with no labels. So basically meaning no supervision by the humans, like it works on its own. Then it also uses anomaly detection to detect something that is abnormal in the data set. Then we have the structured machine learning pipeline. This is like used before like developing. This is used like before developing an effective machine learning algorithm. So first of all, we get the data, we gather the data that is clean, of course, then we perform the exploratory data analysis to analyze and visualize this data. Then we have to prepare the data for the machine learning algorithm by like removing missing data and also performing like feature scaling at that stage. Then we have to like select a certain model, and it's from that model that we train the algorithm. Then we have to fine tune the model. Here we have hyperparameters that are used to optimize the accuracy, and also after that you present your solution to like stakeholders that are concerned. Then you launch and monitor and maintain your system. Then to talk about more of feature scaling, as I had said earlier, it is used to prepare the data before like feeding it into the algorithm. Then we have two techniques used under this. We have normalized data, we have standardized data. So these are the two formulas that you can use. Then in these diagrams, we see non-normalized features where the gradient descent does not directly go to the center. It's in a zigzag form, so which means the data is unnormalized. But then this normalized data shows that the gradient descent moves straight to the center. So we have three key things for machine learning model: a prediction model, a cost function, optimizer. Prediction model is used to predict outcome from various features, of course. Then based on the input of the features, yes. Then we have a cost function. This is used to compare the predicted value, the actual value, to ascertain and calculate the error between those two values. Then we have the optimizer. This optimizes the predicted value to an extent that it should be nearly all the same as the actual value. Then we have models, and their types. We have deterministic model. This deals with no randomness. This is suitable for when prediction errors, of course, are negligible. So which means there should be no chance of any probability in this case, unlike the probabilistic model, which deals with randomness. So an example of this deterministic model, we have a linear regression model that always produces the same result for the same input. So which means there is no randomness. So then for the probabilistic, this deals like predicting rain, or predicting the weather for the future. Like if you want to predict that it's going to rain tomorrow, you'll based on features like the current temperature today, the humidity, and such stuff. Then under probabilistic models, we have regression models, correlation, and other models, of course. Then the regression modeling steps, you have to first, of course, hypothesize the deterministic component, specify the probability distribution, and then after that, it's when you have to evaluate the fitted model, the model that in the non-parametric models, here you're basing on the data to know what the regression should be and how it should look like, because the number of parameters here are unknown. So this one is usually expressed in the form of an equation where y is equal to f of x plus a constant, let's say c, where we do not know what f of x stands for. So that's why we do not know the number of parameters. Then we have 3 steps for implementing this KNN algorithm. First of all, we calculate the distance between all training and training data and testing points. To calculate the distance, you can use either Euclidean's distance or Manhattan's distance, as we shall see on later. Then we find the nearest k neighbors by sorting the pairwise distances. You use the distance between 2 points. Let's say 2 points where one is a training data point and a testing point. Then it's after that you shall get an outcome based on the majority vote. Then, like I said about the Manhattan and Euclidean's distance, in this case for the Manhattan distance, the distance between y and x is go through a right angle between those 2 points, while for the Euclideans it's a straight distance between those 2 points. And this is a formula for finding the Manhattan's distance. Then decision trees are basically used to divide the input data, and it also works on recursion by recursively going back to those features to continue calculating the information gain and the entropy. And it's with that information gain that you arrive at a decision of that certain node that you're going to add onto the decision tree. Yeah, that's the basic understanding. So an example here is that you're trying to predict, will a customer buy a product that is above his pay grade based on features like income, age, and purchasing history. So with that, we use an ID3 algorithm, which is basically used in decision trees based on a certain data set. Basically, this one works with works on 3 steps where where we find the best future based on the value based on the variable with the highest information gain, and with that we find the best split for that best future, still based on the information gain, and also we split the classes based on the previous 2 steps. So of course, as a recursive algorithm, it continues until it meets a stopping condition. And how is it going to stop? And how are you going to set up this stopping condition? The stopping condition occurs when the features in a certain at a certain node have like a same label, and that's when the recursion stops. Then we have tree pruning, which is a technique for like preventing overfitting, and that's it.
Is Atari Brian, and I'm going to take you through the last 3 modules. Yeah, that's module 5, 6, and 7. Yes, my first slide is ensemble learning and random forests. So yeah, taking ensemble learning is just a technique where multiple models are combined to come up with a performance that would be better than individual models. Yes, and ensemble learning has mainly 2 techniques. We have bugging and boosting. Yeah, bugging can also be called bootstrapping. Yeah, under bugging, it's where models are trained using different random subsets of data, and then their predictions are you find the average of their predictions. Yes, and of course in most cases an average of many different models is going to be better than the outcome of one individual model. Yes, then the next technique is boosting. Boosting basically focuses on improving on the mistakes or on the errors or the failures of the previous model. Yeah, so if model 1 made some errors, the next model will try to, do better. Then model 3 will try to solve the errors of model 2. Yes, and like that, like that. Yeah, that's what we call boosting. Yes, and one of the very most popular bugging based algorithms is random forests. Yes, and we talk about random forests here. Yes, random forests, it's a random forest is an ensemble method based on the bugging technique, and yeah, it basically builds multiple decision trees and then combines their outputs. Yes, it's basically the same, feed different models with different random subsets of data and then come up with an average. So that's basically what the random forest is. Yeah, random forest because it's a collection of decision trees. Yeah, it's a collection of decision trees. And then yeah, key features of random forest, or what you can call like the advantages or the impacts. Yeah, the advantages on the next slide. The advantages of random forest are high accuracy and robustness. Then it works well for classification and regression. Then it can also handle nonlinear relationships very well. Then of course the disadvantages, it can be computationally expensive with large data sets. Then also interpretability is lower compared to single decision trees. So here we go to boosting and other boost. Yeah, we already talked about boosting. Boosting is basically training models sequentially such that the next model improves on the mistakes, on the performance, on the failures of the previous model. Yes, and then other boost, which you can call adaptive boosting. Yeah, it's one of the earliest and simplest types of boosting algorithms. It focuses on adjusting weights of data points based on how difficult they are to predict. Yeah, so I normally like to understand things using analogies, and I understood this other boost as a way of you give weight to predictions according to how difficult they are, and then you go ahead to focus on the more difficult things to predict. Yes, So that's literally adaptive boosting. It's more of iterative boosting, because you give weight to predictions or to data points based on how difficult they are to predict. Yes, and then key features of Ada Boost, you can say it combines many weak models into one strong model. Of course, that's, yeah. Then models that perform better are given more importance in the final prediction. Then it works well for both classification and regression problems. Yes, then we go to support vector machines, or what you can call SVMs. Yes, in SVMs, these basically aim at finding a boundary that will separate classes within the widest possible margin. Yes, I went ahead to define margin on my next slide. Margin is the distance between the hyperplane and the hyperplane and then the closest data points. Okay. Then we have support vectors. These are data points closest to the hyperplane. Then hyperplane is the decision boundary separating classes. Yeah. So back to SVMs. Uh, these ones aim at finding a boundary that will separate data points with the widest possible margin, with the widest possible distance, such that these data points can be separated as widely as possible. And types of SVMs, we have linear SVM and then non-linear SVM. Yeah, linear SVM, this is where data points can be separated using a straight line. Okay, such that if there is a data point here, data point here, data point here, you easily draw a straight line, and then, yeah, you can easily acquire a wide range, a wide margin between the data points in question, or the ones that are being separated. Yes. Then the non-linear, this is where, yeah, a straight line can't work, and then they have to be projected into a higher dimension, such that, yeah, within the higher dimension, we shall be able to find a way of separating them linearly. Yeah. Under non-linear SVM, we use a Kernel trick. A Kernel trick can be defined as a mathematical function that maps data into higher dimensional space, making it possible to classify non-linear patterns. Yeah, this basically pushes or projects data into higher dimensional space, since it can't be separated linearly. And then the, let's say, the 2D, maybe if you project it into 3D or higher dimensions, it will be possible, and then to be separated linearly. And to project that, we use what we call the Kernel trick. Of course, common kernels include the polynomial, GRBF, sigmoid kernel, and then the cosine similarity kernel. Yeah. More still about SVM, we have what we call the hyperparameters in SVM. We have the C parameter, hyperparameter, and then the gamma. Yeah, the C can be viewed as a way of controlling overfitting. Yeah, that's just a brief way you can see. Then the gamma controls the distance of influence of a single training point. Yeah, under gamma we have low values of gamma and higher values of gamma. Yeah, and then they are really self-explanatory. Well, we go to data standardization. Data standardization is a pre-processing step where we transform data to have a mean of 0 and a standard deviation of 1. Yeah, this basically ensures that they are on the same scale. It's like taking away the advantage of 1 and you basically judging all the data on the same level. You take them the same level, and here you're handling it on the same level. The importance of data standardization, or it ensures all features on the same scale, preventing larger values from dominating. It improves performance models relying on distance calculations such as the SVM, KNN. Yeah. How to standardize the data? We use the simple formula. You just subtract the mean of the feature and you divide the difference by the standard deviation of the feature. Okay, yeah. Something small to note about this is we use data standardization for algorithms that are sensitive to feature scales, and then it's also not required for tree-based models such as, the random forests and stuff. Lastly, we have the PCA, or the principal component analysis. The goal of the PCA is to reduce dimensionality of the data or keeping information loss to a minimum. Yeah, like I said, I normally like to explain things using an analogy. And I would explain PCA as a scenario where someone is going for a trip and they have to pack the important things. And this way you classify them into, let's say, footwear, clothes, and then foods. Yeah, then you select each from each of the classes in such a way you take small things, but then all the essential things are tackled. Yeah, we have applications, we have image compression, noise filtering, exploratory data analysis. Benefits of PCA, we have speeds up models, improves visualization, dimensionality reduction, yeah, and many more. Yeah, because of time, I'm going to stop from there. Thank you so much.